All right, team, today we're going to talk about 8.4 nonlinear systems. This means we're going to have systems of equations with things that are not necessarily straight lines. So just to kind of get us kind of warmed up here, I want you to solve these 5 equations. Most of them are quadratic. We do have one cubic in there. These problems you'll see embedded in my examples. So this is kind of like the bulk of the work. So go ahead, take a moment, solve these 5, and then we will talk about these 5 and then talk about all of the examples that I have. All right, hopefully these went okay. For the first problem here, notice I do have a quadratic. So first thing I want to do is I want to go ahead and get this set equal to 0, because notice there is a linear term in here, meaning there is a term with an x in it. So at this stage, I'm getting everything set equal to 0, so I scooted the 25 over. You could now do quadratic formula on this, or you could try to factor it. I do see that I could take out a GCF of 5, and kind of really no matter what strategy I choose, it would really be worth my while to go ahead and do that, because now I'm dealing with much smaller, easier to work with values, because I could divide both sides by 5, because that multiplier of 5 has no effect on where it crosses the x-axis. However, it would affect like the shape of the graph, but it does not affect the solution. So now this is what I'm working with. So you could either do completing the square, quadratic formula. I'm pretty sure this guy factors, so multiply to -5 and add to -4 would be a -5 and a +1. So this would yield a solution set of, it looks like -1 and then +5. I'm just putting them in order from smallest to largest. The second one is kind of the exact same idea here. I need to get it set equal to 0. I think these numbers are a lot more user-friendly because I don't have a GCF with the terms here. So now I can try to factor. Or again, you can use quadratic formula if you want, or completing the square. Completing the square would be a little bit ugly on this one since that b value is 1, but you could certainly do it. So here I'm going to multiply to -90 and add to +1. So I'm thinking +10 and -9 for my factors. So that means -10 and +9 would be my 2 solutions. The fourth one is actually quite fantastic. Because there is no linear term, we can go ahead and isolate the item that's getting squared. So we get y squared equals 16. Now let's square root both sides. So this is going to give us ±4 for our y values. The fifth one, now I'm going to tell you here that because we're working with a system of equations, we are working with real solutions. So when I divide both sides by -73, I get some kind of terrible looking fraction over here, -80/73. And when I try to square root this, well, I'm now going to be taking the square root of a negative. So this one has no real solution. It certainly has imaginary solutions, but we are working within the real number system today. So this one would have no solutions. And then our fifth one here, so x cubed equals 1. So this is asking what number cubed is equal to 1. Well, if that was a number squared, we would take the square root. So if it's a number cubed, we're going to take the cubed root. So what times what times what is 1? Well, just 1. So we're going to get 1 as our solution here. All right. So talking about nonlinear systems, I'm going to give you guys 3 options right here. We've got an ellipse, we've got a circle, we've got a line. This is just, a few of many different possibilities that we could choose here. So could you pick a couple of them and see, how could you overlap them or connect them so that they would have 1 solution, 2 solutions, 4 solutions, or possibly no solution? There's lots of right answers just to kind of get you an idea to visually think about what these pictures are going to look like. So for example, if we had something that was 1 solution, pick your 2 favorite shapes. So maybe we'll do an ellipse and a circle, and maybe they're touching just at 1 point right there. Or you could certainly pick either the circle or the ellipse, and maybe it's with a line and it's again touching just at 1 point. So those would be examples of something with 1 solution. Something with 2 solutions, say, would maybe be a circle and ellipse, and then maybe it's kind of looking like a Venn diagram right here where they're touching in 2 spots. Or maybe one of those with a line and it's going through and touching again in 2 spots. Something that would have 4 solutions, well, maybe you would have to use the circle and the ellipse, or it could certainly be like 2 circles, 2 ellipses, something like that, but where we're getting a lot of overlap here. So we could certainly have something like that. And then something that would have no solutions means they don't ever touch. So pick whatever two shapes you want, and maybe they just never touch. Maybe it's something like that. That line, say, is vertical, it's going up and down, and it's never ever going to touch that ellipse. So just kind of keep these in mind for the type of possibilities. If you kind of have an idea of what the equation, what the picture of the equation that we have looks like, you can kind of estimate, and get an idea of what type of solution we should end up with. So here's our first problem. We're going to solve this system of nonlinear equations. This first one is a straight line, and this second one is a circle. So for something like this, we could end up with just one solution, right, where it's just touching in exactly one spot. So maybe, something kind of like that. I guess the initial picture I drew would be an example of no solutions, or we could certainly end up with something that has two solutions. So these are my possibilities. I guess what I'm trying to say here is like this one would never have four solutions, but it could have 0, 1, or 2. So something like this looks a little bit funky. I can't do elimination on this one because I don't have another x squared term and I don't have another y squared term. What I can do though is use substitution. So what that means is I'm going to take this first equation because I can pretty easily make this look like either x equals or y equals, and then substitute that value in for the other equation, the variable in the other equation. It would be less work if I made this first equation look like y equals. So I'm going to take this equation and I'm going to take away negative 2x from both sides. So I'm just rewriting that. It ends up being in slope-intercept form. So now that I know what y equals, wherever there's a y in my other equation, I am going to substitute and plug in negative 2x plus 5. So for my second equation, that would give me an x squared plus. Now, instead of y squared, we're substituting in what we found y to be equal to. So that would be a negative 2x plus 5 quantity squared. And then that would be equal to 50. The goal here is that we now have one equation with only one variable. I don't care if the variable is x or the variable is y. I just care the variable is the same variable. So this is now something that I can solve. So this is going to be x squared plus. Now, make sure you correctly distribute this quantity, negative 2x plus 5 quantity squared. So off to the side, I'll do this in pink. I'm going to write it times itself over here. So negative 2x times negative 2x is a positive 4x squared. This would give me a negative 10x, another negative 10x, and it looks like a positive 25. So adding some like terms together, this is what we end up with. So I'm going to go back, and so I'm going to have x squared plus 4x squared minus 20x plus 25, and set that equal to 50. Let's go ahead and clean up this left-hand side. So 5x squared minus 20x plus 25 equals 50. Now notice here, this is where the warm-up comes in. This is what we solved as the first problem in our warm-up. So you can refer back to that slide. We ended up with x equals negative 1 and positive 5. This means I have two solutions here. And notice negative 1 and 5 would be within the domain of both of these graphs. So I won't say function because the second one, the circle, is not a function, but it's in the domain of both of these. So we're actually going to have two solutions, two ordered pairs that are going to solve it. One that has an x coordinate of negative 1, and then I need to figure out what the y value is. And then one that has an x coordinate of 5, and then I'm going to need to figure out again what that y value is. So what I can do to determine that y value is, well, plug in the x. I'm going to plug in the x to the first equation because that one looks a lot nicer to work with. So I'm going to do 2 times negative 1 plus what is equal to 5. So this is the equation that we're solving. Negative 2 plus y equals 5. That tells me when x is negative 1, the y value is going to be 7. And then let's do the same thing over here with the 5. So 2 times 5 plus what equals 5. This tells me 10 plus y equals 5. So this tells me y is going to be negative 5. So these are the two ordered pairs. Again, an ordered pair has an x and a y value that solve this nonlinear system. Here's a picture of what we have. Here's our circle with radius of square root of 50. And then so that's just a little bit bigger than 7. And then we have our line. So you can see here at the point 5, -5, it's crossing. And then way over here at -1, +7, it's also crossing. So visually, this is what we just solved. We found those two solutions. Let's try another one. So this first one is going to be a circle. And then the second one is the square root equation. So it's going to look something like that. So you can kind of think about what sort of solutions we're going to have. It looks like it could be 0, 1, or 2 solutions for this. So let's try it. Again, I don't have like multiple x squared terms, so one in each equation, and same with the y squared term. So substitution looks like a good method for this one. I already know that y is equal to the square root of x. So wherever there's a y value right here, let's substitute in the square root of x. So we're going to have x squared plus the square root of x squared equals 90. So x squared plus the square root of x quantity squared is going to be x. So this is the equation I'm left with solving. Now, this was our second warm-up problem. So we found out that x is going to be equal to -10 and +9. Let's look at both of these values. If I plug -10 into the second equation right here, I can't take the square root of -10. That is not within the domain of that square root function. So right away, -10 is going to get the boot. Let's look at 9. I can take the square root of 9 for that second equation. And if I go back up to the first equation, I can definitely take 9 squared. So 9 is a value that works. So then to find my ordered pair, this is an x coordinate. So I'm going to plug in 9 and I'm going to see what do I get for my y value when I plug in 9 for my x value. Now you can work with either equation. The bottom one looks a little bit nicer. So I'm going to say y equals the square root of 9. So the square root of 9. Notice I'm not putting that square root on to solve my equation. It's just there. So what's going to happen here is I'm going to end up with a +3. So the 0.93 is going to be my solution. If you wanted to use the first one to solve it, let's just talk about what's going to happen there. I'm plugging in 9 for my x value. So 9 squared is 81 plus y squared equals 90. I'm going to go ahead and take away 81 from both sides. So this leaves me with y squared equals 9. Now I'm running into a bit of an issue here because I am having to put the square root sign on here to solve for this. So I would have to say plus or -3. But notice if I have the -3 as a solution right here and I plug it back into this second equation, I will never take the square root of something and end up with a negative number. So that would tell me to get rid of that negative sign right there. And again, it would only leave me with the ordered pair 9, 3 to solve this system. Here's the picture. So we have our circle here with radius of square root of 90. So a little bit bigger than 9, smaller than 10, and our square root equation. So that line keeps going there, and here's where it starts. So you can see here's the one spot where it intersects. So this is our 0.93. All right, let's take a look at this one. So this first equation is a circle with radius of square root of 17. This second equation is one of the conics that we didn't talk about. The second equation is actually a hyperbola, and it's doing something like this. It's in two separate pieces. So we can either have, I guess, maybe no solution. Actually, I think these would have to intersect. Well, no, the circle, I guess, could be inside. So we could have no solution. We could have 2 solutions possibly, or even 4 solutions, or I guess 1 solution too. So we have a lot of options here for the number of solutions. What's cool about this one is notice each of these equations, each has an x squared term and each has a y squared term. So we could use our elimination method here to solve for one of our variables. I would say since we have an x squared term that each have a coefficient of 1, if I multiply one of the equations by -1, then that lets me add them together and eliminate those x squared terms. So x squareds are going to cancel. Y squared plus 2y squared is 3y squared. And then 17 plus 31, I think, is 48. This was our third one that we had to solve. So let's go ahead and divide both sides by 3. And let's take the square root. So this tells me that the y value is going to be plus or minus 4. So when we set this up, I'm actually going to have my ordered pairs, I'm going to have something for x when y is positive 4, and I'm going to have something for x when y is negative 4. So I need to plug in 4 for x and see what, or sorry, 4 for y and see what x is going to be, and then do the same with negative 4. You can pick either equation that you want to work with. I think the first equation just looks a little bit nicer to me, so I'm going to work with this one. So I'm going to say x squared plus y squared, so this is going to be 4 squared, equals 17, and this is what I'm left with solving. So let's go ahead and take away 16 from both sides. So I'm going to get x squared equals 1. Now when I root both sides, this is going to give me plus or minus 1 for my x value. So notice when y is 4, x could be positive 1, or x could be negative 1. So I'm going to squeeze in another option here. So here's 2 solutions to my nonlinear system. Now let's work with negative 4. So x squared plus negative 4 quantity squared equals 17. Notice this gives me the exact same thing. I'm left with x squared equals 1. So x is going to be equal to plus or minus 1. So I'm going to get the same thing. When y is negative 4, x could be positive 1. And when y is negative 4, x could also be negative 1. So I get these 4 points of intersection. Here's the picture to really look at it. So here's my point 1, 4 and negative 1, 4, and then 1, negative 4 and negative 1, negative 4. So we get those 4 points of intersection. All right, let's take a look at this one. Definitely kind of a big one going on. What I would probably end up doing is rearranging this so that way my x squared and y squared terms are both on the same side. So I'm going to add y squared to the first one, to both sides. And then on the second one, it looks like I'm going to take away the 9x squared. And I want everybody to line up so that way I have everybody in just ready to go and in line. So I end up with this. Now I need to work on elimination. This one's going to make me work a little bit harder. With the 4x squared and the negative 9x squared, I could certainly work with a 36 and a negative 36. That would require me to multiply both equations by a constant. Or if I look at my y squareds, notice I have a 1y squared and a 16y squared. So I could very easily multiply everybody in this top equation by negative 16. So sometimes you have to multiply both things. Sometimes you can get away with just multiplying one. I always err for the least amount of work that I have to do. So now that top equation, everybody gets multiplied by negative 16. And then the bottom equation, I don't have to do anything because I have the positive 16y squared that I want. I always have one positive and one negative with the same coefficient, so that way I can add them together. So I'm going to add my x squareds together and I get negative 73x squared. My y squareds cancel, and then I get, I think that's 80. This was our fourth problem that we had for the warm-up, and this one yielded no real solution. So since this piece right here is no solution, this tells me my two shapes are not going to be intersecting each other. And I'll show you a picture of what they look like. I've got an ellipse right here and then this hyperbola. Again, you don't have to know that that other one is a hyperbola. It's just, kind of cool to see the visualization here because they don't ever touch each other. So that's why there is no solution. So you would just have the empty set for this one. All right, here's my last example. So this one actually looks really, really nice. We have a parabola, and then we have 1 over x, which is a rational function. So we could have multiple points of intersection here. Let's see what's going to happen. This one is prime for direct substitution. If both of these are set equal to y, that means if I do substitution here, I could take this x squared and plug it in for y and end up with x squared equals 1 over x. Now, this is the point where people usually freak out because they're not sure exactly what to do with, just how to proceed with solving this. This is actually a really nice equation to solve. I need to get my x's on the same side. So if I am dividing by x, go ahead and multiply both sides by that x term. Multiplying by x and dividing by x just leave me with my numerator because multiplication and division undo each other. And now I have x times x squared is x cubed. And we found that when we took the cube root of both sides, the cube root is just 1. So x equals 1. So to find out what our other ordered, or what our other coordinate is going to be, let's go ahead and plug in x equals 1 into either equation and see what our y value is. I don't think it really matters too much. I'll plug it in, I guess, to the top equation. So 1 squared is 1. So when x is 1, y is 1. So this one just is intersecting in one spot. And here's our picture. Here's the point 1, 1. So this is kind of just the idea. You could be given any type of function or non-function with the conics, and either using substitution or elimination, you can determine the point or points of intersection. Good luck. Let me know if you have any questions. Your homework tonight is Connect Math 8.4.